So hello and welcome. My name is Jason Harlow. I'm the Associate Chair for Undergraduate Studies here, and I'd like to welcome you to the final colloquium of the year. So I want to start, before I introduce the speaker, I want to just say a big thank you to all the people behind organizing these colloquia, including the Colloquium Committee, Colloquium Committee Chair, and Joanne Magne. So just a round of applause for that. So I'm very pleased and honored to introduce tonight's speaker, Professor Carl Wieman. Professor Wieman got his bachelor's degree at MIT and his PhD at Stanford. In 2001, he won the Nobel Prize in Physics along with Eric Cornell and Wolfgang Ketterle for fundamental studies of Bose-Einstein condensates. But for the past 20 years, Professor Wieman has been heavily involved in physics education research and improving science education around the world. He's the founder of the PhET Interactive Simulations Project, that's the PHET. This is a nonprofit open educational resource that includes over 125 free interactive simulations. In fact, for years we've been using PhET simulations in our own first-year labs and some of our breadth courses in this department, and they're really quite wonderful. From 2007 to 2013, Professor Wieman worked at UBC in Vancouver, where he started the Carl Wieman Science Education Initiative, and he's now based at the Graduate School of Education at Stanford University, where he and his group are investigating things like expert thinking in physics, evaluating and improving undergraduate physics courses and labs, and as the title of his talk says, teaching students to think like physicists. So let's give a warm welcome to Professor Wieman.
So, thank you. It's a pleasure to be actually back here. I think this is probably my third colloquium at Toronto, but there's been a pretty big gap at 25 years or so in the middle, so maybe not two of you remember. So I'll first make a couple of tiny corrections to the introduction. That I've actually been working in physics education research and teaching research for quite a lot longer than 20 years. It was only after I got the Nobel Prize, people started paying attention to me about it. So, anyway, and I also have still an appointment in the physics department, so I'm a strange person who straddles both worlds. So I'm going to talk to you about sort of taking a scientific approach of how to teach students to think like physicists or more like physicists. And so what I'm going to cover today is just first give you an introduction sort of to about the framework of how to think about this and the fundamental educational goal, which I would argue we have for our courses and our teaching. And then I'll show you how to apply, that sort of the basic principles. And then I'll show you how those principles can be applied in various kinds of undergraduate physics courses, and for that matter, other science courses, but I assume people here are physics. And the kind of research we've done actually testing the results in real courses. And then to the extent, if there's any time, I might spend a little here discussing issues of how to scale up to make these things more widespread, and finally try to leave you with some specific thing you can take home tomorrow and teach better in your class based on what the research on learning actually can give you guidance. So, but before I start in that, I want to give you an idea of sort of how I came to get involved in this, in studying, teaching, learning, and physics. And it didn't come actually from my teaching of courses. I mean, I just did the same thing everybody did and that I saw, and I knew it wasn't very effective, but I had no idea how to do anything different about it. Where I really changed my whole thinking about this came from working with my atomic physics graduate students and seeing how they developed as physicists. And I saw there was after a number of years and many students, I saw there was a real fundamental question that baffled me here, which was these students, they didn't get to come into my research lab unless they'd had many years of great success on, exams and physics courses. But when they came to do research, they were pretty clueless about how you actually do physics. And what particularly confused me is the students who were the very best in the coursework and exams so on never turned out to be anything better than kind of middle-of-the-road physicists. And so, but it wasn't some fundamental deficiency in them because they virtually all turned into being good physicists after a couple of years. So I came to think of this as, okay, there's some fundamental question or research question here about how people learn to think, learn to become physicists and think like that. And so I treated it just like a science question. I dug into what we knew about, or what the research showed on how people learn, particularly how people learn physics, which I found there was a significant body of relatively new research at that point. And basically, doing that, what it came out was I found the explanation, this puzzle actually made complete sense. It made me realize there could be much more effective ways to do regular classroom teaching. And then it also got me interested in pursuing this idea of that you could do research on teaching and learning. You could do, do controlled experiments. You could establish underlying principles and so on. So there was a lot like physics. And so for many, many years, I've actually had 2 parallel research groups doing those. The last few years, I've condensed down to just the learning research. Okay, so, now I'm going to move now to sort of the educational goal and how this shapes what I'm going to talk about later, which is, if you ask, okay, so what was it, you try and think about, what was it that my graduate students weren't able to do, had failed to learn from doing well in all these courses? And it really came down to, well, they couldn't think like a physicist when put in a research environment, but that really meant, when I think about it, it meant that there was all these different places where they had to make decisions about, what does this mean? What would be good data to take? What's a good hypothesis of what might be happening? They didn't know how to make these decisions. And so if I step back from that, and I try and get you to step back from that and think about, I'd argue, really the basic goal of what we do in a university education is if we're effective, teach students to make better decisions. It's not better decisions on everything, but this whole set of relevant contexts and situations that we cover in their education, we want them, if we're effective, they will be able to go on in their lives and make better decisions about those sort of situations. And so, if you sort of boil that down to the, individual course or program level, it means, in physics, that first, they have some new problem or question that they're faced with, being able to recognize that, okay, the knowledge and the decision-making process of physics is relevant here, and then recognize how to use the knowledge and the reasoning process of physics to make that decision better. And I want to stress particularly what kind of decisions I mean by that, because it's always issues of decisions with limited information. If you've got complete information as to what to do in the decision, then it's just an automatic procedure. If it hasn't already been replaced by a computer, it soon will be. So these are, what real experts are always doing is making judgment decisions with limited information. And that's ultimately what, when we talk about expertise in a discipline, that's really what it boils down to, is the people can make, better decisions based on the standards of the discipline. So the rest of my talk is sort of, okay, how do we, what's the best way to teach people to make better decisions in physics context, and what's a better way to measure if they're really learning what's important. But because I want to stress this a lot, I'm going to give you 30 seconds to just individually think about the decisions that a physicist makes in solving authentic problems. So I don't mean the back of the textbook chapter problems. I mean a real physics problem one would be faced with, and think of some of the decisions that go into that problem solving. So you have 30 seconds to figure them all out. All right, so hopefully you came up with some reasonable list. I'm not going to take the time to call on you and go through. I'm going to list a few that I think that show up when I do consistently. Of, people talk about what what simplifications or approximations are appropriate. When information's needed and what's irrelevant to the context. Having an appropriate mental model for the problem that sort of guides you and help how to think about deciding it. And oftentimes these come through analogies. And then one that you hear faculty complain about enormous amount, an awful lot of time is having criterion, judging of deciding if an answer is reasonable or not, right? I mean, this is something, now, I list these because pretty much everybody, and well, not pretty much, everybody who does any science would see those as useful. You might, we'll come back to just how much of those actually getting things that students are practicing and being tested on in their actual coursework. Okay, so if we start looking at okay, we want this kind of thinking like a physicist and making decisions about this. It turns out that over the last couple decades, there have been major advances in 3 different research areas that actually give us a very nice complementary input, much better picture of how people learn complex thinking, which in this case, is thinking like a physicist or an engineer and so on. This comes from the cognitive psychologists who look a lot at basic processes of how people think and learn. It comes from brain research, most recently, of looking what's happening inside the brain. And then it's coming from these kind of science and engineering classroom studies that I and others do, and particularly people are looking at this connection now between those 2 areas. And so I'm covering a little of what is involved in this and what people have found. First, I'm going to sort of give the very high-level picture of the basic paradigm of thinking about how this kind of learning is obtained. And so first, I'll make the comparison with the old view of how this kind of learning happened, which frankly is still reflected in the vast majority of how our university courses are taught, is that these brains come into the classroom and they vary in a lot of different ways, and then we immerse those brains in knowledge, and it sinks in to varying amounts, depending on the initial condition of the brain. Okay, so if this is your basic model, and it does underlie, stuff to think about, it really underlies a lot of how we think about teaching at the university level, then the focus of this becomes first the contents of what the knowledge soup is, the curriculum you're going to immerse the brain in. And anybody who's been in faculty meetings knows most of the educational arguments are, do we cover topic A first or topic B, or do we leave topic C out or put it in this course, etc., all about the curriculum there. And then the second is focusing, okay, let's try and get the best brains that the knowledge will soak in the best for, okay? And then finally, if it doesn't work, blame it on K-12. Okay, so what the research on this is showing from these three different areas combined make it very clear that there's quite a different picture here, which is these brains come in the classroom and they're really not that different. And they transform as a result of the educational process and really fundamentally change. And so that the brain actually, in response to intense thinking about something, the brain is actually changed, rewired, and in the process develops new thinking capabilities. And it turns out, just the research shows, that those changes and improvements are much more dependent on actually the teaching methods than they are anything about the specific content, just as a sort of side note. So, and this idea that they have to be strenuously thinking about the subject for an extended period of time, it's becoming increasingly clear that this is basically a biological requirement, that the brain in response to doing this is really making different neuron connections, to a limited extent growing new neurons and putting them into networks. And that's really, and in that process, through that extended thinking process, it's really building up the neuron connections that give you the enhanced decision-making capabilities, enhanced decision-making in that particular context. And we can talk about how general they are as a different issue. But it's so this expertise is quite field-dependent, and it really is built into this rewired brain. And it takes a long time because it's very, it's clear that it's very much like building up a muscle. That if I want to build up this muscle, I've got to use it very strenuously. Using it a little bit, doesn't do any good. I've got to push it to the limit. I've got to do that a lot. And over time, the body says, okay, it's going to make it do that. I'm going to get bigger and stronger, make it bigger and stronger so it can do it better. And so that's what's happening in the brain. And it turns out that for pretty much everybody, it takes comparable amounts of time to do that. And to reach sort of the Toronto physics professor level, it's thousands of hours actually of that. And okay, so just one last thing about this, it's quite recent. We can actually look at the brain while it's learning, and we can actually, these claims I made can be justified by watching that the brain actually changes. This is an example of having two people interpret a medical X-ray image, okay? And the two are a medical student who's just learning about this, and the other one is a very experienced, expert radiologist. And they have them do this inside a functional MRI and look at what's happening in their brains. You can see that both the portions, but also, the brain activation between these two is strikingly different. And, and like I say, people study this over time and see these changes that actually take place as learning. So it really, we really can now quite strong understanding that there's big changes going on there. So then it gets into, all right, so why are these different teaching methods, why do certain teaching methods work better than others? I mean, I'm assuming that all of you have at least some vague awareness that there's this, physics education research out there and claiming certain methods work a lot better than others. And you can, it may not be very clear why or what's behind this, but you can actually understand most of this at a very mundane level. And so I'll start with that, which is think about, if it's in terms of making good decisions, what's the, think about the best way to make good decisions. I'll give you a choice between, one is, okay, being told if you ever encounter this situation, here's the decision should be made, versus actually practicing making the decision and seeing how well it works and getting feedback on how you might make it better, okay? So if you're, this is essentially the idea of a lecture, of telling people what the decision should be, and this is in all the physics education research, it shows the biggest differences. That it's really underlying that is always having the students practice making decisions and get feedback on. So if you're not convinced which is better here, I'll give you an example. You've all, or probably all of you have actually done this experiment, and it's exactly the same thing happening in the brain, okay? Imagine you're in a new city and you want to learn your way around, driving around that new city, okay? So you have one method where you try and learn it by, you want to get from someplace here over to someplace there, and you have somebody sitting next to you that says, okay, this corner, turn right, drive it, and then you go up 3 blocks, turn left, turn right, etc. And you go through getting from one place to another that way, versus, okay, you don't have that person, you have to sit down, look at a map, think of a mental model of how the city works, and as you go through it, actually have to make decisions about where you should be turning, and then you see, okay, this one seemed to work, that one put me in a dead end, that probably wasn't so good, etc., okay? And so anybody's, lots of people have been in that situation, and you know that if you are just being told what to do, you don't learn anything, you just never could reproduce it, never have any sense of the layout, and it's because the neurons weren't doing anything in that process, okay? And so when you get down to all these fancy educational jargon and methods, just think, okay, what are they having students practice decisions with feedback, because that's what counts. Okay, so now I'm going to talk about how those, apply this in teaching in actual physics classes, okay? And so here's basically a summary of all the research and a whole bunch of research on what's important about how to have people learn to make better, physics decisions. And so in the center is the brain has to be practicing the desired thinking, and it's got to get good feedback on that. So in this context, it means it's got to be practicing making these physics decisions, and then the kind of feedback is actually shown it plays a very important role in the learning, but it has to be have very particular characteristics. It's got to be timely, it's got to be specific, and it's got to show people how they can change to do better, okay? And so I won't go into the further research on this. I'll just make the statement that that feedback, which has all these components, has a very large impact on learning. Feedback which doesn't, for example, 2 weeks later finding out you got a 35 on the exam, is pretty worthless, okay? But anyway, so that's kind of key here. But then all of these are all really important factors that have to guide the design of the teaching activities here and go into this design. And these are things that research has shown are just important in practical terms in most courses, implementing these effectively, and their underlying principles that really have to be attended to there. So I'm going to talk a little about, quickly through a few of these things that you may not be familiar with, just so you can understand sort of the key underlying principles, and then I'll give you classroom examples, okay? But I want to say that these, and really the research showing these are important, that you put them in, you get better learning. These really define teaching expertise in a way that was impossible certainly 20 years ago, I'd say, maybe even 10 years ago. But now we have enough research that just like in medicine. We know if there are certain things a doctor does, does right, you're going to get better patient outcomes than other things doctors may have done in the past. We can now say very much the same thing about physics teaching. So, okay, so let me pick a few of these. So let me talk about disciplinary expertise and how its critical role in this. So it's the disciplinary expertise that really guides, okay, what is the expert thinking in physics that you need people to be learning? Obviously, you need a teacher who understands what that thinking is and then builds in what questions or problems or tasks they're going to be thinking about that's going to be exercising the brain in the right way. And so, from my perspective, the best way to get to those is to think about, okay, back what I asked you, thinking about solving a real physics problem, what are the decisions that people make, and then practice those, because in the practice it's, you have to bring, the learner then has to bring in the knowledge and the reasoning processes of physics to answer those decisions, okay? So, I'll just some that I listed before of looking at the problem, like I say, it's some completely new physics thing I'm looking at. So I'm going to start is, okay, what concepts are applicable here that I want to use? What information is important to solving this problem, and there's always a million things in a real problem you can ignore, or you need to actively think what you can ignore and what's important. Mentioned before, what approximations are appropriate, and then based on this, you start thinking about what potential solution methods are good to pursue here, and evaluating them. And then you go through a bunch more, and actually you go through 36 more, which may seem strange, but one of the things my research group is doing right now is really looking at the nature of expertise across different science and engineering disciplines. And what we've been struck by is, how similar the list of decisions is across all those fields, but I can also particularly tell you that there are about 40 that are used in most research science, but I'll limit to here physics, most physics research questions that an expert will go through to solve those. Now, the other thing I want to stress is the importance of having the learner practice actually making the decisions. And we did with Natasha Holmes, who's my super postdoc, who's now at Cornell. We finished, and it's being published now, a study in which she did a controlled comparison between having students do very much the same thing, but in one case they were told, okay, need to have a decision here. Here's what the decision, here's a good decision to have. In the other case, it was going through and giving a lot of scaffolding. They weren't having to invent the whole thing. It's just saying, okay, here's a limited specific decision that needs to be made. You need to make that decision, and then you need to act on it. We put it in a laboratory setting, but act on that decision and see how well it works, okay? And so, they end up spending the same amount of time going through the same kind of stuff, but the difference on subsequent tasks between the ones who'd practiced making decisions was just enormous. I mean, it's almost, it's pretty close to infinite, because you couldn't even make a ratio. And it's for just the reasons I talked about before. Okay, so the embodied in those tasks have to be students actually practicing specifically making decisions. Okay, the prior knowledge and experience, this is sort of what I think everybody can kind of intuitively understand. If this task is going to be hard but doable, it's got to match what the students know and be at the right level. Motivation, you want them to work really hard, you got to think about how to motivate them, convince them it's worth putting in. I have to say, inherently has to be difficult. It has to be take a lot of effort. just because the brain, if it doesn't work hard enough, the brain actually doesn't do the changes that you want to have. But so I'm going to tell you about brain constraints, because this is something that I think most people don't know and don't have much intuition about. There's two things that are particularly pervasive and relevant here, which is, first, it has the issue of working memory. So this is going to be a very quick cognitive psychology summary. When people think about, the researchers think about memory, there's long-term memory. That's what all of us normally think about as memory. It's got this giant capacity and remembers things for very long periods of time. But then when you're learning new things, there's this sort of buffer called the short-term working memory. And this is what the brain, the stuff the brain on short time scales, what's going to be happening in a course, dealing with the amount of new material it can remember and process, goes in through this working memory. And it has a limit of about in the human, has a limit of about 5 to 7 new items, okay? So a very tiny capacity. And it's really the number of things the brain can pay attention to at one time, okay? And new means it's not in long-term memory. And so any additional loads on this thing actually, reduce the processing, reduce the amount of learning. This is fairly easy to study, and so it's been very extensively studied on this, how this works. So, one immediate manifestation of this is that split attention, dividing up that tiny limited capacity, just kills learning. And so if you don't believe anything else that I'm going to say in this talk, except the fact that you need something to keep your students really engaged in the material, or they won't learn anything. This is the bottom line. And so, I'll just tell you, actually, it's harder for you looking from the front to see. I just see one person who's not learned anything because he's been, but I go in the back of lecture halls like this, and you look from the back, and I see, at Stanford, 50% of the students will have their computers open or looking at their cell phones on other things. And frankly, they're just wasting their time and they're wasting the instructor's time. There's just zero happening there as a result because of this fundamental aspect of how the brain works. But there's a lot of other things that are important. I mean, thinking about what you're doing in the teaching. So, obviously introducing some new, additional jargon terms. A lot of times faculty will think, well, I can use this. It's just convenient. If they don't really pick up on what it means, it won't really hurt anything. Turns out, because of this working memory limit, any additional thing somebody would pay attention to hurts, okay? So you have to make an active decision as to whether benefit justifies it. So introducing new jargon, putting up pictures that you're supposed to illustrate something, but you get some nice picture with a bunch of background stuff just because it looks more aesthetically pleasing. Turns out that will hurt learning. If it's interesting enough students to look at it, it uses up working memory. And then finally, the one that students and faculty both, when I tell them this, they get the most excited about is when I tell them, all those nice little jokes, funny jokes or digressions on that interesting little story that talks about, that actually was hurting learning. And the faculty will say, or the students say, oh, but that was the only part I was paying attention to. The only interesting thing. The faculty will say, well, that was the only time students were paying attention. How can that be bad? And, and I point out, yeah, and that's the only thing the students remember from that class, okay? Because it displayed, their attention to that displaced their, capacity for the other stuff. So, so I won't say jokes and interesting stories are automatically bad, but they have to, they have to be fully integrated with the learning and the thinking that you want students to do, or they will actually reduce. And there's a nice paper on showing the danger of seductive details, they call it, in a class in this regard. Okay, so moving along here. The other aspect is how long-term memory works. And, you know, we remembering things isn't everything, but it's certainly, if people don't remember it, it's there's a big loss. So it turns out with long-term memory, the problem isn't so much getting stuff into memory, it's correctly getting it back out, okay? And but what happens with the recall is you put it in a memory, and there's these neuron pathways that link pretty directly, and so it's pretty easy to remember it. But then as you learn new things, that puts in interference. There's new neuron linkages getting put in there. So actually, learning new stuff damages long-term retention of earlier stuff. And so, if you think about the way we teach, it's covered chapter one concepts, problem sets, etc. Some exam, midterm maybe covering that. Done. They've learned chapter 1. End of that, on to chapter 2, 3, and 4. But it turns out, and there's studies showing, okay, but if you measured what they knew about chapter 1 after chapter 4, they know less about it than they did, or they can recall correctly less about it than they could earlier because of this interference of learning new things, okay? And so this is a basic problem in learning and long-term. But it turns out that if you just have regular spaced, spaced recall and application of chapter 1 stuff, they have to think about it again, recall it in some capacity. Basically, that cleans up all those interference terms. And so that's kind of a key, small but important step to realize that you just can't think about chapter 1 being done at the end of chapter 1. You need to come back to those things. In a physics audience, it's easy to explain this. It's very much like doing a quantum measurement. Kills off all the interference terms, okay? So this is this is sort of an important constraint in designing things. Okay, so I want to move on here to a couple of key things about implementation, just because I see, and I'm frankly focusing on things where I see people have heard about doing things and they put them in place without sort of understanding principles and details, and so they don't work. Just the same way that if I wanted to go do a nuclear physics experiment, it wouldn't work because I wouldn't know all those complex little details of implementation, even though I know the basic concepts. And so this one, in fact, I'll say I encountered today, as in many, many other cases, a place where, okay, people were trying to have group, well, I'll get to that. Yeah, no, I'll get to it here. A group activity, and basically they didn't have the right deliverables, and so it wasn't working like they wanted. So what you need is, when they have these practice tasks, the task is important, like I talked about, but then you really have to make it work right, you have to think about what the students have to do and what they have to deliver, and that's really important for defining what they have to do and communicating to you how well they're doing it. And these deliverables you want every student to do, you want them to work in groups, you better have not just a group deliverable, but you have to have an individual deliverables too, because that otherwise it won't ensure that the individual students are doing the thinking you want. So that's just critical for the implementation design. And then I'll talk a little about social learning, working in groups, because again, this is a place where I see so many people, and I have a bunch of examples very recently from Stanford I've seen. Having students work in groups is a great thing, so they just throw them together to work on groups in something, and it turns out it's not a great thing at all. It's kind of a waste of everybody's time, and so you have to understand why and how these can work. And so, I mean, there's a few things. First, just the idea that it could work at all. I hear a lot of faculty have trouble accepting that, gee, talking to a ignorant fellow student is supposed to be more effective than having me, the expert, explain to them all. Or also, then that this could be, talking in groups could be more effective than just having them think on their own individually, because we want them to learn on their own. So, okay, so I will say, yes, it is better, but only if you do it right and you understand what you have to do to make it work right. So first is it has a benefit of efficiency in that you can give students harder problems and they can make, and I'm thinking about in a classroom setting here, harder and therefore more meaningful problems, and they can make progress on them better, both because there's a lot of quick little feedback that, you know, if you've completely forgotten what a Hamiltonian is, but you know a lot of others, but he knows, he can remind you, remember the Hamiltonians, oh yeah, and then you move on, as opposed to being stuck for a long time. I can't run around to every student and check if they got it. So that sort of quick feedback that helps people move forward and spend a lot less time sort of being stuck is one clear optimization. But of course, that only works if you got problems like the one I was seeing at Stanford, where, yeah, really easy, everybody could answer these. It was just stupid to have them as, you know, they're memorized stuff. So anyway, the second is a much more interesting one, which is that, and this is something that's been, because it's so interesting, the cognitive psychologists study quite a lot, is that when people are called upon to explain something or, you know, teach someone else, or even they don't actually have to do it. They just have to expect that they're going to have to do it. It kicks in a different cognitive processing of the material. And so it's really fascinating. You can have people study something a bunch of times. You can test them on it. You can then have two groups. One of them studied a bunch more. The other group spend the same amount of time thinking about how they were going to have to teach it to somebody else. You can measure them on their learning, and the one group has improved, the other one hasn't. So it's a fascinating phenomenon. It's like turning on a overdrive or something in the brain if they have to do that. So anyway, so that's a reason that fundamentally people learn from that process. And you know, I have a pretty well perfected introductory quantum mechanics course now where I just routinely can give them questions where nobody in a group will be able to answer it. They'll talk individually, we'll test them, and they'll talk about it for a couple minutes, and then most people will be able to answer it just because they figured it out. And then finally, the other value to these working groups is, as an instructor, you can take advantage, you can listen in on those discussions, and so you can get, that's the easiest way to get an idea of what's going on in those students' brains, so you can, this critically important targeted feedback, you can do a much better job. Okay, all right, so now move on to showing you how to actually do this in a class. And a typical classroom in this, oftentimes people find easier time doing it in smaller classes, so I'll start with the example of an introductory class this size, and I'll move on later to upper level courses. So anyway, so let's say I was teaching, all of you were all first year students teaching you about electricity. And so the first thing I give you pre-class reading assignment, very specific, targeted particular pages. I'm not expecting you to master electricity. There's basic terms and basic information that you can get better or as well by reading it, so why waste class time on it? So you do that sort of background information. We have developed ways to make sure people actually do it, and we wrote a paper on this after studying, but I'll tell you, you need a little online quiz as part of it, okay? And then I'd start class with a question here. So, you know, here's light bulbs and batteries, and closing this switch, they have to answer what's going to be the how's the brightness of this going to change? I want to make sure everybody's participating, so I have them use clickers. Their cell phone apps do the same thing now. But basically, so individually, they'd have to answer. My computer records who they were and what answer they chose. Now, I see a lot, particularly at Stanford, but I'm sure it's other places, really bad use of clickers and clicker questions. So I want to just sort of tell you, okay, what they do and don't do. So at one level, I can see what people answered up here, so it's useful for me to give a quick snapshot of, okay, do they completely know this stuff or nobody knows it? So there's that guidance. But from the student and the learning perspective, all it's really done at this point is just they've had to commit to an answer in which they have some level of accountability. Now usually they don't count much, if anything, for grades, but they know I'm looking at them, and so that's some level. And basically, if you're called upon, if I say, okay, answer this question, versus if I say, answer this question, write it down on a piece of paper with your name on it, and hand those in, you will think much more deeply about the question in that case, and you'll be more prepared to learn from subsequent things. The same thing's happening here. Okay, so then the learning starts happening. Then I don't show what the vote was. I don't give them the answer. I have them have to talk to the adjacent students in a room like this about what the answer was and why, and then re-vote. And while they're doing that, I'm walking up and down the aisles, listening in on those conversations. Now, in a room like this, I can only sample a small fraction of the groups. Turns out I could get probably 90% of the thinking, though, both good and bad, that happens from that kind of sampling. It's not that variable. And then I go ahead and after they've talked, they've re-voted, then I demonstrate what happens, show them the result, and then have a follow-up summary. So where I talk with the whole class, bring out the thinking and reasoning that was being used, talk about which part of it were right, like physicists, and which part of it were incorrect and why. And I have this emphasized because, again, I see a very common error, and this I had to learn about this from my cognitive psychologist friends. I didn't realize this, is that turns out you don't really learn very much if you got something either right or wrong, and then you're told what the right answer is. Where you really learn is when you get something wrong, and then you understand what about your reasoning was wrong in that case. That's where really all the learning happens. And so this idea of, a bunch of you missed this, here's the right answer, that's just not very useful at all. Whereas going over, let's tease apart what reasoning was used to get this wrong answer, what things people were overlooked, so you can avoid doing that in the future. Okay, so back to the goal here, thinking like physicists with practice. So, if you think about what they have to do in this process, they're making a bunch of decisions. They're deciding, they have to formulate, think about what their basic concept of electricity is and how it interacts in light bulbs, and what that, and what would happen in this situation. So they're formulating and, thinking about conceptual model. They're having to test the conceptual model both against, what arguments of other students and what's going to happen. They're critiquing the reasoning of themselves and others through this process. And so, if I just gave you this set of things here and I replace this with, electric light bulb with, pion scattering, you'd see, yeah, that's what physicists are doing all the time, right? And so this is very much, at a reduced level, but the same kind of reasoning and practicing the same kind of thinking that physicists would do. And they're getting multiple forms of feedback to improve that. They're getting it from the interactions with their fellow students and how they respond. They're getting it from comparing their predictions with what actually happens. And they're getting it from me, the now much more informed expert, teacher, on talking about their solutions. So basically, that's sort of showing you how we're, this example is a way to how you put in place these basic mechanisms of learning to get better results. Okay, so when was I supposed to end? Now? Okay, so I'm running very slow. So I'm going to give you I'm just going to quickly give you a few examples of data and then stop for questions. So this is one where they're looking at, introductory physics, testing how well students can apply the concepts of force and motion to simple real-world situations like a physicist would to make predictions, okay? And so the reason I like it, they have a lot of instructors over a lot of sections, and there's a good test for measuring this. And so they got an average. These are scattered around on this particular test about 0.3, which is, we have data from lots of physics courses now using this measure, and that's pretty typical for a well-taught lecture course. Then they all switch to this scientific teaching where their sections of 40, a whole bunch of them, but so students are working in round tables in small groups, working through problems with the instructor circulating around. And then after they switched, it was the next years, they measured again. And basically, the average and almost every individual one has just doubled. And so the point that this really makes is that you get the same instructors, but the only thing they've changed is their teaching methods, and basically the learning doubled. So, it's really and this and other data backs up this idea that what really dominates the learning outcomes is the teaching methods of the instructor, not how they look, what jokes they have, etc. Here's doing the same ideas, actually the same teaching method I used for electricity, where they applied it to a bunch of computer science courses at UC San Diego through somebody who worked with me, and they looked at their drop and failure rates, and basically the bottom line is, again, they've got the same people with different teaching methods, and they have a third the failure rate across these courses, and it's improved all of them as a result. Okay, then finally, I want to talk this one. Those and most of the research is looking across entire courses, okay, and the learning outcomes. This was an experiment just to measure the learning that happens in the classroom, okay, in the lecture setting. And so it was done at UBC in their big introductory physics for engineers course. And so, class about this size, or section about this size. So we had two sections, measured a whole bunch of measures to show they were really identical. And then the comparison was, the control was this, somebody who'd taught this many times, but a pretty standard lecture approach with good student ratings. And the experimental class was somebody who was a relatively new PhD in physics, but they'd been through my training program in these teaching methods, okay? And using things like I illustrated with the electricity example. And so the two instructors, before they started, agreed on exactly what material to cover. And this, one of the reasons for this was people always think, oh, you can't possibly cover as much material. Well, if you optimize, we wanted to say, if you optimize coverage in ways we know how to do it, how close could you really come? And so that was a clear thing of covering the same material in the same amount of class time. So it was 1 week of class time. And then the students had a pop quiz, so they didn't do any studying for this outside of the timing of session. Didn't do any studying outside. It was just to measure, okay, what did they learn from coming to these classes? And so basically, usually I take time to give a bigger build-up to this, but I'll jump ahead to say, so this is the histogram of results. So the score on the test versus the number of students. You can see very different distributions between the experimental class and the standard lecture class. It's actually, the differences are bigger than you probably guess, because this was, to keep this clean, we used a fairly carefully developed multiple choice test. And so just by random guessing, on average, a student would get 3, okay? So you really have to think the learning is how much above 3 they are. And so from that perspective, you realize just how little the students actually learn from a lecture. And if you don't believe this, I'll challenge you. Anybody can do an experiment in their own class like this. I'll point out 25 years ago I did in mine, and it wasn't so different. So in my beautifully clear lectures. And so how little the students are really learning from a lecture here, and how big a difference is with these other methods. Also stress that, notice the whole distribution moved up. So, this isn't something, it's in a method that just works for the best students or just for the worst students. It works for the students with a human brain, because it's the way the human brain learns. So, okay. Okay. And then I'll just mention, because people ask me at various times, so most of the research has been on introductory courses. My group and a few others has been looking at this in advanced courses. And bottom line is, yeah, it works there too. This paper gives a whole lot of detail about the details of designing the activities and how to actually implement this in upper division courses where you got smaller classes and they're much more mathematical and they're working in small groups here. But I'll just leave you with the basic structure of these classes, which is, generally speaking, seems to be a pretty good structure for implementing this kind of active research-based learning in any environment. Is they do something to prepare for class, and that can vary. And then during class, you'll have some activity that they'll be working through for the whole class, where they'll work for 10. 10's a good goal, 15's pretty long, unless a pretty advanced class. Work in small groups, working on something where they're answering individually, but discussing and challenging it, where the instructor's walking around, circulating, monitoring what they're doing, but then stopping class after 10 minutes to summarize where people are, give students general feedback on things they're struggling with, what they need, information they need to know they don't have, answering questions, sort of bringing, we talk about resynchronizing the students so they aren't getting too far out of sync and working through this. And then they return and continue working through the activity that way. And basically, okay, we get data. Yeah, it works. They learn more. They can think better like physicists. At Stanford, we now converted a bunch of the mainstream major courses like this. And there's a couple of immediate things. Attendance in class went way up. That's the first thing faculty noticed. But students are really positive about it. And actually, the faculty are really positive about it, too. They find once they've learned to teach this way, it's just much more rewarding than lecturing. And so they're continuing to do this, as are most of the faculty, or all the faculty who changed at UBC in Colorado. Okay, so I'll just finish with, I know that a lot of people, a lot of faculty who've been teaching this way, have this question and about, gee, I learned this way. How can it be so bad? This is the answer. For 2,000 years, people thought bloodletting was the best medical treatment, and the only way to distinguish that is actually you have to think scientifically, and scientifically means you got to have a proper comparison group. And so, the only way you can make this claim that it worked for you is to have a clone twin who went through the other method, and show that you learned just as much. I'm absolutely certain what the result would be. But so, it's not that you weren't successful, it's that you would have been more successful if you'd had a different way of teaching. So, yeah, so I will, with that, we'll skip all this other stuff, which you can, I'll make sure my slides are available. You can go read it if you want. And there'll be a lot of time for questions. So, okay.